Imagine a world where the sky is always on fire, not just red, not just bright, but searing. A place where the horizon glows with a permanent sunrise and the atmosphere is being stripped away grain by grain like sand in a storm. That world exists, and it's being eaten alive. This is a type of planet known as a hot Jupiter, a gas giant orbiting so close to its star that its atmosphere is boiling off into space. It orbits once every Earth day or less, locked in a death spiral around its host. The heat is unbearable, thousands of degrees, and the gravity from the nearby star tugs relentlessly at its gaseous envelope. Astronomers first discovered such doomed planets when they noticed faint trails of material bleeding off into space. These planets are literally forming a tail, not unlike a comet, as their atmospheres are pulled into long, glowing streams by the star's radiation. Over time, this process will strip them bare. Some might be reduced to rocky cores. Others may disappear entirely. This phenomenon tells us a lot about how stars and planets interact over time. It challenges old models of planetary stability and migration. Why would a gas giant ever form so close to a star? The current theory is that they don't. They migrate inward, pulled by gravitational tugs over millions of years, until they reach a point of no return. And here's the haunting part. We've caught some of them right in the act. Using telescopes like Hubble and TESS, scientists have observed atmospheric loss in real time, spectral fingerprints showing hydrogen, helium, and heavier elements trailing behind these burning worlds like smoke behind a torch. One of the most studied cases of this is a planet that loses the equivalent of billions of tons of gas per second. It's like watching a planet dissolve. We don't yet know how long such a planet can survive, but we do know this. It offers a window into one of the most dramatic ends a world can face, not by collision, not by freezing, but by slow, fiery disintegration, death by starlight. Far beyond our solar system, in the direction of the constellation Leo, there's a small, faint red star known as K218. It's the kind of star you'd likely overlook in a telescope, quiet, cool, and unassuming. But orbiting this dim sun is a planet that has captured the attention of astronomers around the world. Its name is K218b, and it might be wet. Not with rivers or lakes or polar caps like we see on Mars, but with something far more profound, an atmosphere filled with water vapor, and beneath that possibly an entire ocean wrapped in hydrogen and mystery. Discovered in 2015, K218b didn't initially stand out. It's larger than Earth, about 2.5 times its size, and nearly 9 times as massive. Too big to be a rocky world like ours, but too small to be a full gas giant like Neptune. It exists in a middle category of exoplanets, a sub-Neptune, a kind of world we have no direct equivalent for in our own system. But what changed everything was what came next. In 2019, scientists pointed the Hubble Space Telescope toward K218b and detected something no one had seen before, the spectral signature of water vapor in its atmosphere. And more than that, it was located within its star's habitable zone, that fragile ring of space where the temperatures could allow liquid water to exist. That single discovery instantly elevated the planet from just another data point to something closer to a dream. Then, in 2023, the James Webb Space Telescope followed up. What it saw was astonishing. In addition to water, the planet's skies appeared to contain methane and carbon dioxide, molecules that together raised a tantalizing possibility that the atmosphere might be chemically imbalanced in a way that, on Earth, is associated with life. Scientists call this a biosignature candidate. It's not proof, not even close, but it's enough to whisper a question that's haunted us for centuries. Could something be living out there if K218b is what some researchers suspect, a Hycean world, short for hydrogen-rich and ocean-covered? It would be a planet with an immense liquid sea beneath thick clouds where the pressure and chemistry are nothing like Earth. But high above that ocean, in the upper atmosphere, temperatures and conditions might be just right. Warm, stable, watery. A place, perhaps, where tiny life forms could float freely, feeding on chemical nutrients and drifting through alien clouds. We don't know what lies beneath those veils of gas. We can't see the surface, if there even is one. But in K218b, we see a mirror held up to possibility. A reminder that Earth-like life might not need Earth-like conditions. That habitability isn't a narrow corridor, but a wide and wild frontier. And maybe, just maybe, there are other skies, red and dim, filled with vapor, where something is watching back, or simply existing quietly as it always has. Picture a world where mountains shimmer not with snow, but with the gleam of crystal, where the bedrock isn't granite or basalt, but something far rarer, compressed, hardened carbon. Deep beneath the molten surface, time and pressure have forged something almost unthinkable, a landscape of diamond. This is the haunting idea behind carbon planets, exotic worlds that may form in star systems rich in carbon but poor in oxygen. In our own solar system, Earth was born from a cloud where oxygen dominated, giving us a world built from silicates and water. But change the recipe, tip the balance, and chemistry begins to write a different story. In theory, a carbon-rich disk around a young star could give rise to a planet where graphite replaces granite, where carbides line the crust, and where, in the crushing heat of the deep interior, diamonds grow not as rare gemstones, but as geological layers, vast, cold, and eternal. We may have already found a candidate. Orbiting the star 55 Cancri, just 40 light-years away, is a world called 55 Cancri E, a planet so hot it glows with infrared light, its surface likely molten. It's twice the size of Earth, but nearly 8 times as massive, suggesting a dense, compact core. Early models hinted at an interior layered with carbon, enough perhaps to form diamond under immense pressure. And though newer measurements have complicated that picture, the idea has lingered, not because we've confirmed it, but because the physics makes it possible. What would such a world look like? You wouldn't walk its surface. Temperatures likely exceed 2,000 degrees Celsius. Volcanic activity might be constant, the crust in flux, rivers of glowing liquid carbon oozing through fractures. The skies could be dark with soot and carbon-rich gases, thick with heat and fury. But buried deep, past the fire, past the fractures, miles down, lies a possibility. Diamond, forged not in beauty salons or deep mines, but by the planet itself, through eons of weight and time. The very idea bends our imagination. On Earth, diamonds are rare treasures, symbols of wealth and permanence. But in a universe where carbon is plentiful and pressure is relentless, they might be mundane, the planetary equivalent of granite. It's a humbling shift in perspective. And yet, it's more than geology. Carbon planets remind us that alien doesn't always mean unfamiliar in form. Sometimes it means familiar things used in wildly unfamiliar ways. The elements we know, carbon, iron, silicon, can build cathedrals we've never seen, mountains that shine, cores that crackle with unimaginable strength, continents that glint under alien suns. We may never set foot on such a place, but with each strange signal, each odd density reading from distant stars, we add another fragment to the map of what's possible and what might be waiting, glittering in the dark. High above the scorched horizon of an alien world, the winds howl at 2,000 miles per hour. They scream across a dark sky filled with shimmering vapor, twisting through superheated clouds of silicate particles. And then, as if conjured by some infernal storm, shards of glass begin to fall, sideways. This is not science fiction. This is a real planet, and what it endures defies even our wildest visions of hell. It's known in scientific circles as a type of ultra-hot Jupiter, a gas giant orbiting so close to its star that its dayside temperature can climb above 1,800 degrees Celsius. That's hot enough to vaporize metal and melt rock into gas. The atmosphere is not just hot, it's a forge, a place where elements are stripped, recombined, and hurled across the sky in storms more violent than anything Earth has ever seen. One of the most famous examples is a planet orbiting a star slightly smaller than our Sun, only a few million kilometers away. On this world, the extreme heat on the star-facing side creates a stark imbalance. Silicate particles, essentially the ingredients of sand and glass, are lifted into the atmosphere where they condense into droplets high in the sky. But on the night side, where the temperature drops, not to cold, but to merely less unbearable, these droplets cool and harden, forming tiny, sharp crystals of glass. Then come the winds. Supersonic jet streams rip through the atmosphere, driving the glass shards sideways at breakneck speeds. These aren't gentle drizzles or peaceful flakes. This is horizontal rain made of cutting edges, a storm that would shred metal, let alone any fragile probe we might dream of sending there. The planet is tidally locked, meaning one side always faces the star while the other lies in endless night. That contrast between relentless fire and muted darkness fuels the planetary chaos. It's a system in constant imbalance, with energy perpetually surging from one hemisphere to the other. And still, through this madness, we learn. By studying the way starlight filters through the atmosphere of such planets, telescopes like Hubble and James Webb can detect the fingerprints of silicates and metals, revealing the composition of clouds that should not exist, in weather that shouldn't be possible. In doing so, we stretch the limits of planetary science. We redefine what an atmosphere can be. We watch the very sky turn to glass. These worlds are not habitable, they are not friendly, but they are extraordinary. They remind us that the universe is not built for comfort, it's built for extremes. And somewhere out there, beyond our gentle blue earth, lie planets where the air itself cuts like a blade, and the rain falls like shattered mirrors from a sky on fire. In the quiet dawn of a distant world, two shadows stretch across the ground, not because of tall mountains or giant moons, but because overhead there are two suns rising in tandem, one bright and yellow, the other smaller and redder, climbing the sky side by side. It's not a scene from science fiction, it's real, and it's stranger than anything Star Wars ever imagined. For decades, astronomers wondered whether planets could even exist in binary star systems, places where the gravitational pull of two suns might tear any world apart or fling it out of orbit entirely. The math seemed messy, the models unpredictable, but in 2011, all that changed. That's when NASA's Kepler mission confirmed the first planet orbiting a pair of stars. Since then, we've found many more, and now we know planets can, in fact, orbit two suns, not just survive there, but thrive. These are called circumbinary planets, and their orbits are unlike anything we know in our own solar system. Instead of tracing a path around a single anchor point, they move in elegant loops around a constantly shifting center of gravity. The stars themselves dance in a tight orbit, and the planet moves around them both, gracefully navigating a cosmic ballet of light and motion. The most famous of these is Kepler 16b, a gas giant, roughly the size of Saturn. If you stood on a solid surface there, though it's likely a gas world with no such terrain, you would see two suns rise and set in intricate patterns, sometimes together, sometimes apart. Some days might last weeks. Some shadows would twist in ways our minds can barely picture. But these aren't just novelties. Circumbinary planets open a new frontier in the search for life. Because if rocky planets can exist in stable orbits around two suns, and there's no reason to think they can't, then the number of potentially habitable worlds in the galaxy could be far greater than we once believed. The double sunlight might lead to extreme seasons, complex climate patterns, and beautiful alien skies. Plants, if they ever evolved there, might have to adapt to two wavelengths of light. Nights might be shorter, or far, far longer. We once imagined such worlds as fantasy. Now they are data points, measurements, spectra, real. And they remind us that the architecture of star systems isn't fixed, it's playful. The universe is more creative than we gave it credit for. And somewhere out there, under twin suns, a planet spins in quiet balance, proving that even the most cinematic dreams can turn out to be true. Imagine standing on the edge of an alien world where the sky is never clear, where no sunlight ever fully breaks through, and every horizon fades into a dense, endless mist. The air is thick, the colors muted, the surface, if it even exists, hidden beneath layers of vapor. This is a planet wrapped in mystery, not because we haven't looked, but because we can't see through its fog. Astronomers call it a sub-Neptune, a planet larger than Earth but smaller than Uranus, cloaked in an atmosphere so dense and opaque that light struggles to escape. One of the most intriguing examples we've found is a world that defies our best instruments. Even under the gaze of the James Webb Space Telescope, its atmospheric signature remains stubbornly featureless, as if the planet itself is choosing to keep its secrets. This kind of planetary enigma challenges everything we thought we knew about exoplanets. When light from a host star passes through a planet's atmosphere during a transit, we expect to see absorption lines, chemical fingerprints that reveal what the air is made of. But for this world, those lines are flat, silent, as though the planet wears a veil we can't pierce. What causes this? The leading theory is that its atmosphere is filled with haze, thick layers of photochemical smog created by complex reactions between sunlight and atmospheric molecules. On Earth, we see this in polluted cities. On Titan, Saturn's largest moon, it's a permanent golden-orange cloak. But here, the haze might be even more extreme, muting all signals, absorbing all clues. Some researchers think this fog hides a deep ocean beneath, a vast liquid layer, perhaps hundreds of kilometers thick, resting on a solid core we'll never glimpse. Others suggest a dense, hydrogen-helium envelope, masking a more exotic interior. Whatever the truth is, we only know one thing for sure. This planet refuses to show its face, and in that refusal, it becomes all the more fascinating. We're used to thinking of exploration as a process of revelation, of stripping away mystery. But some planets remind us that mystery can be part of the story, that even with the best tools, some places will always resist easy answers. In a universe full of dramatic extremes, lava worlds, glass storms, frozen giants, sometimes the strangest place of all is the one that hides in silence, shrouded in fog, offering no reflection and no reply. Picture a planet where there are no continents, no islands, no dry land at all, just water, stretching in every direction, as far as the eye could see. No coastlines, no mountain ranges, only an unbroken ocean, hundreds of kilometers deep, cloaked in clouds and bathed in faint starlight. This is the vision of a true ocean world, a planet where liquid water doesn't just fill lakes and seas, but covers the entire surface in a global, all-encompassing flood. In our solar system, we have icy moons like Europa and Enceladus, which may have oceans beneath layers of ice. But a fully aquatic exoplanet with no land masses and no frozen crust takes this idea to another scale. Scientists believe such planets could be common across the galaxy, formed beyond the snowlines of their star systems, then migrating inward, carrying with them vast stores of water. One candidate lies about 100 light years away. Its size and mass suggest a density too low for rock, too high for gas, pointing instead to a composition dominated by water. Not just surface water, but layer after layer. A high-pressure ocean above, a deeper, denser layer below, and possibly even exotic forms of ice locked in place by crushing internal forces. This isn't the water we know. It's water reshaped by alien gravity and heat, forming structures and states of matter we've never encountered firsthand. On such a planet, sunlight might filter through the upper atmosphere into a pale, clouded ocean. Beneath the surface, it would grow dark quickly. Pressure would build with impossible speed. At a depth of 100 kilometers, the water might begin to compress into forms of ice that are solid not because of cold, but because of pressure. These so-called Ice 7 or Ice 10 layers might form the base of the ocean, a strange, crystalline seafloor above a hidden core. Would life be possible here? Perhaps, but only in a narrow zone, a twilight layer near the top, where light and chemistry interact. Microbial life, if it ever took hold, could float freely in the upper reaches, drawing energy from the faint rays of a distant sun. Deeper down, warmth from the core might drive hydrothermal vents, as they do in Earth's oceans, potentially sparking even more complex ecosystems in total darkness. We often imagine life needing land, needing stability, but Earth's oceans are a reminder that life began in the water, not on the shore. And if planets like these are as common as we suspect, the galaxy may be filled with liquid worlds, vast, silent, and teeming with possibilities beneath their endless waves. To them, land is the alien concept, and silence, not shorelines, is home. Some planets live too fast. They're born, drift inward, and spiral so close to their stars that they barely survive. Their days are short, their skies a furnace, their fates already written. These are the hell planets, worlds that orbit so close to their stars, they're constantly on the edge of vaporizing. We've found many of them. They complete an orbit in mere hours or a few Earth days, circling their stars at distances so small they'd fit well inside Mercury's path. From that proximity, the heat is relentless. Temperatures soar to thousands of degrees Celsius, hot enough to melt iron, vaporize rock, and strip atmospheres away molecule by molecule. Their surfaces, if they have any, are likely seas of molten minerals. Lava flows may stretch for thousands of kilometers. Clouds, if they exist at all, could be made of vaporized metals or silicates, forming strange mineral mists under the blaze of permanent daylight. And on some of these worlds, the heat is not the only threat. The stars they cling to often blast them with powerful radiation and stellar wind, tearing at their atmospheres and exposing their cores. In extreme cases, the planets begin to evaporate, not just lose gas, but physically shrink, like a stone boiling away under a blowtorch. These planets come in different sizes and types. Some are rocky, Earth-like in mass but utterly scorched. Lava planets, baked dry and glowing with thermal energy. Others are gas giants, pulled so close to their stars that their outer layers swell up and begin to drift off into space. Some may even leave behind nothing but a rocky remnant, the skeletal remains of what was once a giant. The existence of these hellish orbits challenges our models of planetary formation. Most planets likely form farther out, where things are cooler and calmer. So how did these worlds get so close? The answer lies in migration, gravitational interactions, sometimes with other planets, sometimes with the disk of gas and dust they formed in, that slowly drag them inward over millions of years. It's a slow death, but a spectacular one. In some systems, we've caught planets in the act of decaying, their orbits tightening year by year. Eventually, some may fall into their stars entirely, consumed in a final burst of radiation, their mass returned to the fire that once gave them form. We call them hell planets, because it's the only language we have for such extremes. But for all their violence, they're part of the universe's quiet math, a reminder that not all systems are stable and not all worlds are meant to last. Some are born to burn. At first glance, it looks like a star with a faint blur beside it, an optical smudge, a trick of light. But as astronomers looked closer, they realized what they were seeing wasn't an illusion. It was a planet, and it had a tail, like a comet. In some distant systems, planets orbiting perilously close to their stars are shedding material so rapidly that it streams out behind them, forming long, delicate trails of gas and dust. These aren't icy comets from the outer reaches of a solar system. They're rocky worlds, or even gas giants, melting and evaporating in real time. These tails are made of silicate particles, hydrogen, helium, or heavier elements, depending on the planet's composition. The intense radiation from the nearby star heats the atmosphere or surface to extreme temperatures, lifting particles upward until they're caught in the stellar wind and blown away. One of the most striking cases is a planet smaller than Mercury, orbiting its star in less than a day. It's so close that its surface likely reaches 2,000 degrees Celsius, hot enough to boil rock. That rock vapor then expands into space, creating a dusty tail that trails behind the planet like smoke. Observations suggest this world may be losing hundreds of thousands of tons of mass every second. Eventually, these planets may disappear altogether, whittled down to nothing by the very star they orbit. What we're witnessing, in a sense, is planetary erosion on a cosmic scale, not over geological epochs, but over mere millions or even thousands of years. The shape of the tail can also reveal surprising details. Some curve dramatically, tracing arcs behind the planet's orbit like a painter's stroke. Others flicker and pulse, expanding and contracting in rhythm with solar activity. They're not just passive trails, they're dynamic, sculpted by magnetic fields, stellar winds, and orbital speed. These comet-like planets are more than astronomical curiosities. They challenge our assumptions about planetary lifespans, about the line between planet and debris. They blur the boundaries of what a planet can be, and in doing so, they offer something rare, a glimpse of destruction as it happens, a fleeting chapter in a planet's life caught in the act of vanishing. Imagine a world where one side never sees darkness and the other never sees light. A place where the sun hangs frozen in the sky, motionless, searing one hemisphere with eternal day while the other lies in unbroken frozen night. This is not a poetic metaphor. It is a real and common outcome of physics, the natural state of many exoplanets across the galaxy. These are the tidally locked worlds. Just like our moon always shows the same face to Earth, many exoplanets orbiting close to their stars become gravitationally locked, always turning the same side toward their sun. For planets orbiting small, dim stars like red dwarfs, which emit less light and require habitable planets to orbit much closer, tidal locking is almost inevitable. At first glance, that seems like a deal breaker for life. One side scorched, the other frozen. How could anything survive? But the reality is more nuanced and far more fascinating. In the blistering daylight zone, temperatures can soar high enough to vaporize water and cook rock. The sky would be brilliant, the ground parched, the atmosphere swirling with heat. On the night side, everything freezes. Oceans, air, even carbon dioxide. A desert of ice and silence. But between these two extremes, along the Terminator line, the thin band where night meets day, something astonishing might happen. There, temperatures could be moderate. Winds could circulate heat from the day side to the night side, softening the harsh contrast. Giant planetary jet streams might howl around the globe, distributing energy and maintaining dynamic weather systems. In that twilight belt, under a dim orange or red sun permanently fixed near the horizon, conditions could become stable and even habitable. Some models suggest that cloud cover on the day side could reflect enough heat to keep it from boiling over, while greenhouse gases on the night side could trap warmth and prevent total freeze-out. It's a planetary balancing act, precarious but possible. Tidally locked planets also offer strange views. The sun would never rise or set. In the middle of the day side, it would shine directly overhead forever. On the Terminator, it would hover on the horizon, casting long, permanent shadows. And on the dark side, eternal night, broken only by starlight and auroras. These worlds remind us that habitability doesn't always mean Earth-like. Life, if it exists, could evolve in narrow ribbons of twilight, feeding on gradients of heat and light, adapted to rhythms unlike anything we know. Plants might always face one direction. Winds might shape entire ecosystems. Civilizations, if they ever arise, might be born in the Shadowlands, where fire and frost meet in delicate equilibrium. In the grand diversity of planets, tidally locked worlds are no outliers. They are expected, common, maybe even the rule rather than the exception. And if so, the story of life in the universe might be a story not of sunshine, but of shadows. Drifting alone through the galaxy, surrounded by endless dark, there are planets that orbit nothing. No sun rises to warm them. No star lights their sky. They move silently through interstellar space, cold, invisible, and utterly free. These are rogue planets, and they may outnumber the stars themselves. Unlike most planets, which form and remain within the gravitational pull of a parent star, rogue planets are castaways. Some were likely born in star systems, but were later ejected, flung into the void by chaotic interactions with other planets or passing stars. Others may have formed alone in the darkness, born from collapsing clouds of gas that never ignited into stars. However they came to be, the result is the same: a planet with no sun. What does that mean for the surface of such a world? Without sunlight, temperatures would plummet to unimaginable lows. The surface would be frozen solid, the atmosphere, if one existed, locked down in layers of ice. But inside, things could be very different. Even without a star, a rogue planet might still have internal heat, left over from its formation or generated by the decay of radioactive elements. If it has a thick enough atmosphere or an insulating ice shell, that heat could be trapped, maintaining a warm interior. And if there's water buried beneath the surface, it might stay liquid. Not in oceans under open skies, but in hidden pockets beneath kilometers of ice, a subsurface sea in total darkness. In fact, some scientists believe rogue planets could harbor conditions suitable for life, protected by rock, pressure, and geothermal warmth. Life that never sees light. Life that evolves not in cycles of day and night, but in endless twilight. Rogue planets are hard to find. Without the glow of a nearby star, they don't reflect or block light in the ways we typically detect exoplanets. But their gravity still acts, and in rare moments, when one passes in front of a distant star, it can bend the starlight just enough to be seen through a phenomenon called gravitational microlensing. So far, we've detected only a few, but models suggest there could be billions in our galaxy alone. Silent travelers, cold refugees, planets that drift between the stars like forgotten worlds, each carrying its own story, its own chemistry, its own version of isolation. In the cosmic balance between light and dark, these are the wanderers, lost, unbound, and hauntingly real. And if life can survive there, then the universe is even more resilient than we imagined. There are places in the lava planet's universe where the ground is not solid, where the very surface of a planet is in a constant state of eruption, glowing, seething, moving like water. These are where oceans are made not of water, but of molten stone, and the landscape is a living, burning tide. We've discovered several candidates for such worlds, most of them orbiting extremely close to their stars, so close that one side, the star-facing hemisphere, becomes a literal magma sea, heated beyond the melting point of rock, while the night side remains cooler but still hostile. These planets are often tidally locked, with the same face always turned toward the star, creating a permanent inferno on one half and a strange, sullen twilight on the other. One such world is thought to have lava tides, waves of molten rock that shift as the planet's gravitational and thermal stresses deform its surface. Winds made of vaporized minerals blow across the sky, cooling into clouds that might condense as stone rain. The air itself could carry sodium and silicon, the atmosphere not a gas in the traditional sense, but a plume of vaporized crust. It sounds like science fiction, but it's all grounded in hard data, spectral readings from space telescopes that pick up the chemical fingerprints of vaporized rock, thermal maps that show extreme temperature gradients across the planet's surface, and orbital patterns that match the predictions for heat-blasted close-in orbits. The formation of these worlds is just as fascinating as their appearance. Lava planets likely begin as terrestrial, rocky bodies, not unlike Earth, but over time, the gravity of their parent stars pulls them inward. As they migrate closer, their surfaces begin to melt. The very skin of the planet liquefies. Mountains become waves. Craters become whirlpools of fire. And beneath that molten crust, possibly an iron core, struggling to hold the planet together under immense thermal strain. Volcanoes might erupt endlessly. The planet may never cool. It may never rest. Some models suggest that the lava might circulate, rising on the hot side, flowing toward the dark side, then cooling and sinking in a kind of rock cycle not seen on Earth. This circulation could maintain active geology for billions of years, long after the planet should have gone silent. The lava planets are inhospitable, violent, and dazzling, laboratories of planetary extremes. They show us what happens when matter is pushed to its limit, when the idea of land becomes fluid, when the concept of a horizon flickers in waves of liquid fire. In a universe filled with water worlds, gas giants, and frozen moons, lava planets are a reminder that not all heat gives life. Some of it simply burns forever. We're used to thinking of planets as layered things, a crust, a mantle, and deep at the center, a dense core that holds it all together. Even in the case of gas giants like Jupiter or Saturn, most models assume there's something solid at the heart, a rocky or metallic core hidden beneath countless layers of hydrogen and helium. But what if that's not always true? What if some gas giants have no core at all? This idea isn't just theoretical. It's been seriously considered as astronomers study the internal structures of gas giants both in our solar system and beyond. Some exoplanets we've observed appear to have such low density, so puffed up and diffuse, that they challenge the standard model of planetary formation. Their mass is spread out over enormous volumes, with no clear sign of a heavy center. How is that possible? The prevailing explanation lies in formation and fate. Most planets begin with a solid seed, a core of rock and metal that gathers gas around it. But in the chaos of a forming system, collisions and heating can disrupt that structure. In some cases, the intense pressure and temperature deep inside the planet might cause the core to dissolve into the surrounding fluid envelope, vanishing not by explosion, but by chemical blending. In other cases, a gas giant might form directly from a collapsing cloud of gas, skipping the solid phase entirely. This kind of gravitational collapse similar to how stars form, could lead to a planet that is gas all the way down. No rocky heart, no molten center, just hydrogen and helium, slowly growing denser as you descend, but never becoming truly solid. The implications are huge. A planet with no core would behave differently in terms of magnetism, internal heat, and atmospheric chemistry. It might lack a strong magnetic field. Its winds could be deeper and more chaotic. Its response to tidal forces from nearby moons or stars could be less stable. In other words, it wouldn't just be strange on the inside, it would act strange on the outside too. And because we can't dig into these planets directly, we rely on light, on spectroscopy, gravity measurements, thermal readings, and the subtle way a planet wobbles as it moves. It's detective work on a cosmic scale, and the clues keep pointing to the same unsettling possibility, that not all planets have hearts. Some may be endless, a sky that deepens into cloud, that deepens into pressure, that deepens into darkness, with nothing waiting at the center, but more of the same. In a way, it makes them feel less like planets and more like storms without end. Giants, yes, but hollow, filled with motion, but not with solidity, with presence, but not with anchor. And yet, in their emptiness, they remain majestic, a reminder that in the universe, not everything that looks massive is built on something strong. Some things are vast simply by expanding and never stopping. At first glance, it doesn't make sense. You measure the mass of a planet, it's not especially heavy, maybe a bit more than Jupiter. But then you look at its size, and it's enormous, bloated, swollen, far larger than physics says it should be. The numbers don't line up. The planet seems too light for its volume, too airy for its appearance. These are the inflated planets, gas giants with mysteriously puffed up atmospheres that make them appear much larger than they ought to be. Some of them are so large they rival small stars in diameter, yet their mass remains modest. They're low-density giants with atmospheres that have expanded outward like cosmic balloons. Scientists have struggled to explain them because under standard planetary models, gas giants should compress under their own gravity. Their size should be tightly related to their mass. But inflated planets break that rule. So what's going on? The leading suspect is heat, not from within the planet, but from its star. Most inflated planets orbit extremely close to their host stars, where intense radiation constantly bombards their atmospheres. The energy heats the upper layers, causing them to expand like air in a hot air balloon. These planets can be tidally locked, with one side always facing the star, leading to extreme temperature gradients and powerful winds that circulate heat around the globe. But heat alone may not be enough. Some models suggest additional mechanisms, like ohmic heating, where charged particles in the planet's atmosphere create electrical currents as they move through magnetic fields, generating extra heat that seeps down into the planet's depths. Others propose tidal heating, caused by the gravitational pull of nearby moons or the star itself, constantly kneading the planet like dough. Whatever the cause, the result is the same: a planet with a giant bloated radius, often with less than half the density of water. You could theoretically take one of these worlds and drop it in an ocean, and it would float. Inflated planets are fragile. Their atmospheres are weakly bound and often leak into space, especially if the planet orbits too close to its star. Some may be caught in a slow process of evaporation, losing mass over time, drifting toward a fate similar to that of comet-like planets with tails. Yet for all their instability, they offer a glimpse into planetary diversity. They show us that mass alone doesn't define a world, that size, structure, and environment are equally powerful sculptors. They also force us to rethink what a gas giant is. Not all are dense and compact like Jupiter. Some are swollen and strange, brief balloons in the long life of a solar system, stretching their skies until the pressure breaks and they collapse, shrink, or disappear. They are planets in flux, and that makes them one of the most vivid examples of how alien the universe can be, even when it's made from the same ingredients we know. Every so often, the universe delivers a quiet contradiction, something that simply shouldn't be there. A planet that breaks the rules, a world that, by every simulation and theory we've built, shouldn't have formed, and yet does. These are the impossible planets, exoplanets, that defy the models we use to understand how planetary systems are born and evolve. One of the clearest examples is a gas giant found extremely close to a small, dim star, a kind of planet that shouldn't have been able to form in the meager disk of gas and dust such a star can offer. According to classical formation theory, there simply isn't enough material that close to the star to create something so massive. And yet, there it is, orbiting every few days, bloated and burning. In other cases, we've discovered super-Earths with ultra-short orbital periods, circling their stars in less than a day, often so close they skim the stellar surface. These planets should have spiraled into their stars long ago, consumed by gravity or radiation. Their presence suggests either that they're newly arrived, or that something is missing from our understanding of orbital decay. There are planets in binary systems where the gravitational dynamics are so unstable we never expected long-term orbits to persist, yet some of these worlds have circled their twin suns for billions of years, in calm, graceful loops. There are even planets orbiting white dwarfs, the burned-out remnants of dead stars. These systems should have been annihilated during the star's death throes, and yet somehow planets remain or reassemble. One of the most puzzling findings is the existence of planets with strange combinations of mass and radius, too dense for their size or too large for their mass. Some may have massive cores wrapped in only thin layers of gas. Others might be hollow-seeming giants, bloated beyond explanation. These outliers challenge the very way we infer internal structure from external measurements. The fact that we keep finding these anomalies tells us something important. Our models are incomplete. They work well for many systems, including our own, but the galaxy is vast, and nature plays by no fixed script. Sometimes planets form in chaotic environments. Sometimes they migrate in strange ways, encountering and surviving events that should have destroyed them. And sometimes they teach us that what we believed was impossible simply wasn't imaginative enough. Every new impossible planet adds a brushstroke to the cosmic portrait we're trying to paint. Each one is a challenge and an invitation to look again, think differently, and accept that in a universe of hundreds of billions of stars, the exceptions may be as common as the rules. We rarely see them, but they shape everything. Magnetic fields are the invisible scaffolding of planetary life, shielding atmospheres, deflecting solar wind, and stabilizing climates. On Earth, our magnetic field protects us from cosmic radiation, guides compasses, and dances across the poles in glowing auroras. But what about alien worlds? Do they have magnetic fields too? And what would those look like? The answer, slowly emerging from data and theory, is yes. Some exoplanets likely have magnetic fields, and in some cases, they might be even stronger or stranger than our own. The generation of a magnetic field depends on a planet's interior. It needs a conductive fluid, like molten iron or metallic hydrogen, in motion. On Earth, that fluid is in the outer core. For gas giants like Jupiter, it's a massive layer of metallic hydrogen swirling under intense pressure. The rotation of the planet turns this internal motion into a global magnetic shield. Some exoplanets, particularly massive gas giants orbiting close to their stars, are expected to have powerful magnetic fields. In fact, they may need them, because the closer a planet is to its star, the more it's bombarded by stellar wind, streams of charged particles that can strip away atmospheres over time. Without a magnetic field, many close-orbiting planets might be left bare, dry, or vaporized. Interestingly, we've begun to detect signs of exoplanetary magnetism, not directly, but through radio emissions and the behavior of surrounding plasma. In one case, astronomers observed a strange bending in the stellar wind as it passed by a planet, suggesting the presence of a magnetic bubble, a magnetosphere large enough to carve space around the world like Earth's does. There are even hints that magnetic fields could affect habitability. A planet in the habitable zone with liquid water and a stable orbit might still be uninhabitable if it lacks a magnetic field, because over time it would lose its atmosphere and be exposed to lethal radiation. Conversely, a planet slightly outside the Goldilocks zone might remain viable if its magnetic field traps heat and protects the surface. Magnetic fields also lead to one of the most beautiful phenomena we know: auroras. On alien worlds, these could be far more intense than on Earth, glowing not just at the poles, but perhaps across entire hemispheres, ignited by powerful stellar flares. Red dwarfs, in particular, are known for violent outbursts. A strong magnetic field might mean the difference between destruction and spectacle. We don't yet know how common these fields are, but as our instruments improve, we're beginning to glimpse the invisible architecture of distant planets, not just their size, orbit, or composition, but their force fields, their shields, their silent defenses. And in a universe full of harsh radiation, collapsing stars, and high-energy storms, that invisible shield may be one of the most important features a planet can have. Not just for science, but for survival. When we imagine life beyond Earth, we tend to picture planets, rocky worlds in the habitable zone, bathed in the glow of a steady sun. But nature doesn't always follow that script. Sometimes, the most promising places for life don't orbit stars at all. They orbit planets. These are the exomoons, and some of them might be even more promising than the worlds they circle. We know that moons in our own solar system already hint at habitability. Europa, Enceladus, and Titan, all moons of gas giants, show signs of subsurface oceans, organic chemistry, or thick atmospheres. If these features can arise here in our quiet corner of the galaxy, there's every reason to believe they can arise elsewhere, and perhaps more dramatically. The key lies in energy. A moon orbiting a massive planet can be kept warm, not by sunlight, but by tidal forces. The gravity of the host planet stretches and compresses the moon's interior, creating frictional heat, enough to melt ice, sustain subsurface oceans, and drive volcanic activity. It's a constant internal engine, powered by gravity rather than light. Now imagine that same mechanism applied to a larger moon, one Earth-sized perhaps, orbiting a giant exoplanet in the habitable zone of its star. There, the moon receives both stellar light and planetary tidal heating, a double source of warmth. Add a protective magnetic field, possibly shared with the planet itself, and you have a compelling recipe for life. Astronomers are actively searching for these worlds. The first strong candidate, a potential Neptune-sized moon, was detected in 2017, orbiting a Jupiter-like exoplanet. Though its nature is still debated, the discovery opened the door to a new frontier. that moons could outnumber habitable planets and in some cases outperform them, and moons offer other advantages. Their tidal cycles could stir oceans and nutrient flows. Their skies might hold double eclipses, one from the planet, another from distant stars. Their surfaces might glow with reflected light, their nights lit not by moonlight, but planet light, the soft, colorful glow of their host looming large in the sky. In science fiction, we've imagined places like Pandora from Avatar, lush moons with exotic ecosystems suspended above giant gas worlds. But science is beginning to catch up. We now understand that these environments are not just plausible, they might be common. And while we haven't confirmed a habitable moon yet, each new discovery brings us closer, not just to new types of planets, but to a whole new class of worlds, not planets, not stars, but something in between, something orbiting in the shadows of giants, quietly collecting heat, chemistry, and time. Maybe the first alien life we find won't come from a planet at all. Maybe it will come from a moon, listening, waiting, circling in silence. If life exists beyond Earth, how would we recognize it? We might never see its oceans or forests or creatures directly, but we might see its breath. That's the idea behind biosignatures, chemical traces in a planet's atmosphere that hint at biological activity. On Earth, life has transformed the air, oxygen, methane, carbon dioxide, ozone, all in unusual balance, shaped not by geology or chemistry alone, but by living processes. And if life is doing the same on distant worlds, we might be able to detect it from across the stars. For years, this was a theoretical hope, but now, with the arrival of telescopes like James Webb, that hope has become a target. The key is transit spectroscopy. When a planet passes in front of its star, a small fraction of starlight filters through its atmosphere. That light carries information, tiny absorption lines like fingerprints that tell us what gases are present. It's delicate work, requiring extraordinary sensitivity, but it has already begun to bear fruit. One of the most promising discoveries so far is on K2-18b, a planet in the habitable zone of a red dwarf star. The James Webb Space Telescope detected water vapor, carbon dioxide, and hints of methane, a mix that on Earth could point toward life. Though the signals aren't conclusive and non-biological explanations exist, it's the first real detection of multiple potential biosignature gases in a planet's atmosphere. Another target is TRAPPIST-1e, one of 7 rocky planets orbiting a nearby ultra-cool dwarf star. While definitive biosignatures haven't been found yet, the TRAPPIST system is ideal for study. The planets are small, temperate, and close enough for detailed observations. As more data comes in, we may soon be able to rule out or confirm atmospheres and search for imbalances that hint at something more. Scientists are especially interested in non-equilibrium chemistry, gas combinations that shouldn't exist together unless something is constantly replenishing them. On Earth, the coexistence of methane and oxygen is a classic example. Methane should quickly break down in an oxygen-rich atmosphere. The only reason it stays is because life keeps producing it. But there's caution too. False positives are a real risk. Volcanoes can emit methane. Stellar radiation can split water and create oxygen. Planets with unusual surfaces or compositions might mimic biosignatures without any biology at all. That's why context is everything. Planetary mass, temperature, orbit, stellar activity, all must be considered to understand what we're really seeing. The hunt for atmospheric biosignatures is just beginning. Each detection is a puzzle, and we are learning to read the chemical poetry of distant skies. The tools are improving, the targets are growing, and somewhere out there, perhaps, a planet is quietly exhaling, not into a void, but into a telescope's waiting eye. And in that breath, we might one day hear the first whisper of a living world. We've come a long way since the first exoplanet discovery in the 1990s. Today, we've cataloged thousands. We've found hot Jupiters, super Earths, lava worlds, and ocean planets. We've glimpsed atmospheres, measured chemical fingerprints, and imagined alien weather. But one goal still hovers just out of reach: the dream of finding a true Earth twin. A small, rocky planet in the habitable zone, with an atmosphere we can study in detail. A planet where life could exist, or already does. To reach that next level, we'll need new eyes on the sky, and the most promising among them are two ambitious missions, LUVOIR and HABEX. LUVOIR, the Large UV's Opticals or IR Surveyor, is a concept for a massive space telescope, possibly with a mirror up to 15 meters wide, dwarfing even the James Webb. It would be capable of imaging Earth-like planets directly, not just as transits across stars, but as tiny points of reflected light. LUVOIR could analyze dozens, even hundreds, of potentially habitable exoplanets, breaking their light into spectra and searching for biosignatures, surface oceans, cloud cover, and more. Where James Webb sees the shadows of planets passing in front of stars, LUVOIR could see the planets themselves, orbiting beside the star like pale blue dots in miniature. And with its powerful instruments, it could observe in multiple wavelengths, from ultraviolet to near infrared, opening a far broader window into atmospheric chemistry. HABEX, or the Habitable Exoplanet Observatory, is a smaller but more focused mission. Its primary goal is direct imaging of Earth-like worlds around Sun-like stars. HABEX plans to use a unique technology called a star shade, a giant, flower-shaped shield that would fly tens of thousands of kilometers ahead of the telescope, blocking out a star's light while letting the dim glow of nearby planets shine through. It's a simple idea with enormous implications, turning the blinding light of a star into manageable darkness so the planets around it can emerge. Both Le Voir and Habex aim to answer one of the most profound questions in science. How common is life in the universe? But they also offer something deeper, the ability to study alien worlds as worlds, not just as data points. To map their weather, seasons, and maybe even surface colors, to detect how their atmospheres change over time, to begin building not just a catalog of planets, but a geography of the galaxy. These missions are still in the proposal and planning stages. They represent the next generation, the instruments that could launch in the 2030s or beyond. But they are more than dreams. They are blueprints, and if funded and built, they could change everything. Because if life is out there, it may not be sending signals. It may not build civilizations or spacecraft. It may simply breathe and let its light scatter into space. And we, with Le Voir or Habex, may finally be able to see it. For every exoplanet we've found, there are countless more we haven't. Most of the galaxy remains uncharted, trillions of worlds orbiting hundreds of billions of stars, each shaped by its own collisions, chemistry, and chaos. And somewhere out there are planets so bizarre, so unexpected, that they lie beyond anything we've yet imagined. The strangest worlds may not be the ones we know, but the ones still waiting to be seen. We've already been surprised many times. Planets that rain molten glass, worlds lit by two suns, gas giants puffed up like balloons, and lava planets spinning in permanent daylight. None of these were predicted before we found them. They were discovered first, explained later. So what's next? What kinds of planets might be out there, just beyond the reach of our telescopes? Some scientists speculate about mirror worlds, planets with the same mass and orbit as Earth, but with wildly different chemistry. Imagine a planet where life evolved using silicon instead of carbon, where oceans are made of methane or ammonia or even supercritical fluids, where clouds float above seas of exotic liquids under thick, colored skies. Others imagine dark planets, worlds so coated in light-absorbing material that they reflect almost nothing, rendering them nearly invisible. These might be hot Jupiters wrapped in soot-like compounds, appearing as tiny dips in starlight or flickers of heat against the cosmic background. We may have already missed some, simply because they're too dark to detect. Then there are the hypothetical crystal planets, worlds formed almost entirely from a single mineral under pressure, like sapphire or diamond. or plasma planets, so close to their stars that their atmospheres are partially ionized, glowing with ghostly auroras that wrap the entire planet like a shroud. And some possibilities are even stranger. Worlds that orbit black holes lit by distorted starlight from distant suns, or planets that exist in trinary systems tugged in complex figure eights by three competing stars, or rogue planets with bioluminescent life glowing faintly in the endless dark, never touched by daylight. As telescopes grow stronger and data deepens, we'll start to catch glimpses. A strange wobble in a star's movement, a spectral signature that doesn't make sense, a flicker of light that fades too fast. And when we do, we'll remember that our understanding of planets is still young. Earth, Mars, Jupiter, these are just local examples. The universe is experimenting far more widely. It's building worlds we haven't dared to name yet. The strangest worlds are still out there, waiting in silence. And one day, they will surprise us all over again.